Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today, we are taking a deep dive into Unit 14, Semiconductor Electronics. We'll be looking at the application of junction diode as a rectifier. Our mission is simple: to make this concept so clear that you understand it perfectly and score maximum marks in the exam. Okay, so let's start with a question, something you see every single day. When you plug your phone charger into the wall supplies AC, alternating current. But your phone battery, it runs on DC, direct current. So why do we need that bulky adapter box between the wall and the phone? Why can't we just plug thin wires directly in?
That is true. It always feels like an unnecessary step. Is it because the AC from the wall is just too strong for the phone?
It is about control, not just strength. And here's a surprising fact that really gets to the heart of it. The AC current from our walls oscillates 50 times per second. That's 50 hertz, right?
Right, 50 hertz.
But a full-wave rectifier circuit, which uses this diode, actually produces an output voltage that pulses 100 times per second.
Wait, 100 hertz?
Yes. We take a 50 hertz input and get a 100 hertz output.
How is that possible? It feels like we are somehow doubling the frequency. How does that happen? And why is that useful?
Exactly the right questions. We must explore how this seeming doubling happens. Let's get to the core idea first. The simplest idea is this. We need to convert the bidirectional flow of AC to the unidirectional flow of DC. And the semiconductor diode, it acts as a perfect one-way valve for current. When voltage is applied correctly, we call it forward bias, it lets the current pass. But when it's applied in reverse bias, it blocks the current. Simple.
Okay, so a one-way valve. I like that.
Let's use an analogy. Imagine AC power is a water pump that pushes water forward and then pulls it backward over and over.
Okay, pushing and pulling.
Now, we install a one-way check valve in the pipe. That's our diode. During the pump's forward push, the valve opens and water flows.
And during the backward pull?
The valve slams shut instantly.
Ah, so the water only ever flows in one direction, even though the pump is trying to pull it back.
Precisely. The result is that the current always flows to the load in only one direction. It converts the oscillating motion into unidirectional pulses.
So the diode automatically filters out the wrong direction of current.
Exactly. This solves the fundamental mismatch we have. AC is great for long-distance transmission, but DC is mandatory for our circuits. And these little semiconductor diodes, they replace the old, bulky, hot vacuum tubes that used to do this job.
Right.
So for a mental image, picture the AC sine wave going up and down. The rectifier's job is to either chop off the negative part or flip the negative part upwards. Either way, the entire wave is now above the zero axis, always having the same polarity.
Okay, that visual helps a lot. Chopping or flipping.
Now, let us see how insert formally defines this concept, building on our one-way valve idea.
Okay.
Could you read out the definition for us?
Yes, it says, from the VI characteristic of a junction diode, we see that it allows current to pass only when it is forward biased. So if an alternating voltage is applied across a diode, the current flows only in that part of the cycle when the diode is forward biased. This property is used to rectify alternating voltages, and the circuit used for this purpose is called a rectifier.
Perfect. That is the precise exam-safe wording. Now let's break down the two main circuits. First, the half-wave rectifier. It's very simple. Just one diode in series with a load, let's say R sub L. So when the AC has a positive half cycle, the diode is
forward bias.
Correct. So it conducts current, and we get an output voltage pulse across the load. But then when the AC voltage enters the negative half cycle,
the diode becomes reverse biased. It doesn't conduct.
Right. We consider the tiny reverse current to be negligible. So the result is output voltage is only present during the positive half cycles. We are just chopping off the negative half completely.
But that sounds very inefficient. We're throwing away half the energy.
It is inefficient, absolutely, which is why we have a better design. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now for the full-wave rectifier, this one is much more clever. It uses two diodes, D1 and D2, and this is important, a center tap transformer.
A center tap transformer? What's that? Why is it so special?
That's the key. The center tap is a connection made at the exact middle of the secondary coil. This means the voltage at the top end of the coil is always perfectly out of phase with the voltage at the bottom end.
So when the top is positive, the bottom is negative.
Exactly. So in the first half cycle, let's say the top is positive. This makes D1 forward biased, and it conducts. D2 is blocked.
Okay, so current flows through the load.
Yes. Now, the second half cycle, the polarity flips. The top becomes negative, and the bottom becomes positive.
So now D1 is blocked,
Yep.
and D2 conducts.
Precisely. And here's the brilliant part. The circuit is wired so that the current from D2 flows through the load resistor RL in the exact same direction as the current from D1 did.
Oh, I see. So no matter which diode is on, the current in the load is always flowing one way.
You've got it. So we get an output pulse during the positive input cycle and the negative input cycle.
And that's where the frequency doubling comes from. A 50 hertz input gives 100 pulses per second at the output.
Absolutely. The full wave output frequency is double the input frequency. And this is very useful.
Why is 100 hertz better?
Because the gaps between the pulses are much smaller.
Yeah.
This makes the next step, filtering, much, much easier.
Filtering.
Yes. See, the output we have now is still pulsating. It's not a steady DC. It goes up and down. We call it pulsating DC.
And electronics don't like that.
Not at all. They need smooth, steady DC. So we need to add a filter. And the most common filter is just a large capacitor connected in parallel with the load.
And the capacitor's job is to smooth out those pulses.
Exactly. The capacitor charges up to the peak voltage during the pulse. Then as the pulse starts to fall, the diode turns off, and the capacitor slowly discharges through the load, keeping the voltage high.
So it fills in the valleys between the pulses.
Perfectly put. It fills the valleys. This smooths out the ripple and gives us nearly steady DC. And this whole process is vital for what comes next in our unit, like using a Zener diode for voltage regulation. It needs a stable input to work properly. Now let's talk about two silent killers, common mistakes that can lose you marks in the exam.
Okay, I'm ready.
First one. The wrong idea is that a forward bias diode is a perfect conductor, like a wire with zero resistance.
I can see why someone would think that. It's supposed to let current pass easily.
It does, but it's not perfect. The correct idea is that a diode always has a small voltage drop across it. For a silicon diode, it's about 0.7 volts.
So I have to subtract 0.7 volts when I'm calculating the voltage across the load?
Precisely. You must account for that 0.7 volt drop. It's not a perfect short circuit. It takes a little energy to open the gate.
Okay, got it. 0.7 volt toll. What's the second mistake?
The second one is about the output right after the rectifier, before the filter. The wrong idea is thinking the output of the rectifier is already steady DC. The correct idea is that rectification only makes the voltage unidirectional, but it is still pulsating.
Ah, pulsating DC. That word is important.
Very important. The filter is what converts pulsating DC into steady DC. The rectifier gives direction, the filter gives stability. Never confuse them.
So rectifier output is pulsating DC. Filter output is steady DC.
You've got it. Now let's lock this in with some memory anchors. First, a simple phrase. The diode is the one-way street for current. Easy to remember.
The one-way street for current. I like that.
Second, a gesture for the filter. Hold your hand flat and move it up and down like a wave. That's pulsating DC.
Okay.
Now, slowly flatten the movement of your hand. That's the capacitor smoothing the wave. Remember, the capacitor charges up on the peaks and fills the valleys.
Charges on peaks, fills the valleys. Got it.
And finally, a mnemonic for forward bias. When does the diode conduct? Remember PPNN, P side to positive, N side to negative. PPNN for forward bias.
That's a good one, PPNN.
All right, let's summarize with the three most crucial facts for your notes. 1. Rectification is converting AC to DC using a diode's property of allowing current to flow only when it's forward biased. 2. Full-wave rectifiers are more efficient than half-waves, and they double the output pulse frequency. For example, 100 Hz output for a 50 Hz input. And 3. The rectifier's output is pulsating DC. A capacitor filter is essential to smooth this into a usable, steady DC. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROF Sam, right?
Yes, ProfSam.com. All the best for your exams.